Well, hello and welcome to our course on algorithms and data structures. We're going to have a very interesting time going through this material. I'm going to give you a little bit of an orientation to some of the basic stuff in the course today in this first lecture, and then we'll start to get into the material. And so we're going to be using data structures and abstractions with Java, Carnot and Henry, their 5th edition. And I'll make sure that there's a link to this text that you can be looking at it. And it really is a fairly relatable and friendly introduction to data structures and implementation, as I'm sure you'll get a chance to see. And there's a fair amount of resources that come along with it. There's the publisher's textbook homepage, there's student resources, and then they have these things called video notes. And so for probably about 2 or 3 per chapter, there's a video note that's relevant. So a pre-recorded video that you can go ahead and sample and get some more hands-on information in addition to this video that's going more or less chapter by chapter. And this is just a quick look at all those video notes that go along with all of the various chapters, and also with the Java interludes, which is another part of what they do with the material here. And so here's a synopsis of the material in the textbook and the things we'll be covering. So there's 30 chapters, and there's 9 different Java interludes that the course is on data structures and algorithms, but you need to really implement that with a language. And so we're implementing that with Java. And so that's the reason why we need to get specific, and those Java interludes will help along that line. Okay, with that, we'll go ahead and do an introduction, and then we'll do a preface. And I think you'll see why these two things are fairly useful. And so let's just give some motivation and perspective into what data organization is as we look around us. You can see that there's various ways that people organize things. Say if you stop in the store, went to the back of the line to wait for a cashier, the line organizes people chronologically. The first person in the line was the first person to be served and to leave the line. Eventually, you would reach the front of the line and would leave the store with a bag containing your purchases. The items in the bag were in no particular order, and some would be of the same kind. And so that's a different type. Do you see a stack of books or a pile of papers on your desk, perhaps? It's easy to look at or remove the top item of the stack, or to add an item to the top of the stack. The items in the stack also are organized chronologically, when the item added most frequently is on the top, and the items added first are on the bottom. So another area would be, say, a to-do list. And so each entry in the list has a position that you might or might not be important to you. You may have written them either as you thought of them, in their order of importance, or alphabetically. Then you decide the order. The list simply provides a place for your entries. Another thing is a dictionary. A dictionary is an alphabetical list of words and their definitions. You search for a word and get its definition. If your dictionary is printed, then the alphabetical organization helps you to locate a word quickly. If your dictionary is computerized, its alphabetical organization is probably hidden, but it still speeds up the search. And then, well, speaking of computer, you have organization of files into folders or directories. Each folder contains several other folders or files. This type of an organization is hierarchical. If you drew a picture of it, you would get something like a family tree or a chart of a company's internal departments. These data organizations are similar and are called trees. And finally, you can think about a roadmap that you use to get away, say, for example, for a weekend trip. The diagram of the roads and the town show you how to get from one place to another. Often several ways are possible. One might be shorter, another faster. The map has an organization known as a graph. And so here, these are just giving you some ideas of some data organization approaches. So let's now apply that towards computers. And so computer programs also need to organize data. They do this in ways that parallel the examples we just cited. So programs can give us a stack, a list, a dictionary, and so forth. These are ways of organizing data and representing it by an abstract data types. And so an abstract data type, or ADT, is a specification that describes a data set and the operations on the data. Each ADT specifies what the data is stored and what the operations on the data do. Since an ADT does not indicate how to store the data or how to implement the operations, we can talk about ADTs independent of any programming language. In contrast, a data structure is an implementation of an ADT within a programming language. So a collection is a general term for an ADT that contains a group of objects. Some collections allow duplicate items, some do not. Some collections arrange the contents in a certain order, while others do not. We might create an ADT bag consisting of an unorganized collection that allows duplicates. It could be a grocery bag, a lunch bag, or a bag of potato chips, if you will. Suppose you remove one chip from a bag of chips. You don't know when the chip was placed into the bag. You don't know when the bag contains another chip shaped exactly like the one that you just removed, but you don't care in the situation. If you did, you wouldn't store your chips in a bag. A bag does not order its contents, but sometimes you want to order things. An ADT can order their items in a variety of ways. The ADT list, for example, simply numbers the items. The list then has a first item, a second item, and so forth. Although you can add an item to the list, end of the list, you can also insert an item at the beginning of the list or between existing items. Do so numbers a list of items when you add something. Additionally, you can remove an item at a particular position within a list. That's a position of an item in the list does not necessarily indicate when it was added. Notice that the list does not decide when an item is placed. You did make that decision. So in contrast to that, the ADT stack and queue order their items chronologically. When you remove an item from a stack, you remove the one that was added most frequently. When you remove an item from a queue, you remove the one that was added the earliest. Thus, a stack is like a pile of books. You can remove the top book or add another book to the top of the pile. A queue is like a line of people. People leave a line from its front and join at the end. Some ADTs maintain entries in a sorted order if the items can be compared. For instance, strings can be organized in alphabetical order. When you add an item to an ADT sorted list, for example, the ADT determines when to place the item in the list. You do not indicate a position for the item as you would with an ADT list. The ADT dictionary contains a pair of items, such as a language dictionary contains a word in its definition. In this example, the word serves as a key that is used to locate the entries. Some dictionaries sort their entries and some do not. The ADT tree organizes its entities according to some hierarchy. For example, in a family tree, people are associated with their children and their parents. The ADT binary search tree has a combined hierarchical and sorted organization that makes locating a particular entry easier. The ADT graph is a generalization of the ADT tree that focuses on the relationship among its entities instead of a hierarchical organization. For example, a road map is a graph that shows the existing roads and distances between towns. So in this course, we're going to show how to use and implement these data organizations. We'll be assuming that you already have some level of Java, and there's some special Java interludes that will help you to focus on relevant aspects of Java that might be new to you and how to handle these exceptions. There's also some refresher material in the text if you want to get a chance to look at that. And so I'd welcome you to get a chance to review that. Okay, the next section we're going to talk about is in the prelude, and we'll talk about how to design classes, specify methods, and write Java interfaces. Using interfaces and writing comments to specify methods are necessary for our presentations of ADT. So that ends the introduction, and we'll just move right into this prelude, and you'll get a chance to see a little bit more context for the material in the course. Here's the material in this chapter. We're going to be talking about encapsulation, inheritance, and polymorphism, and that's going to be important. And so here's just a quick summary of the textbook chapter contents. And so we'll roughly be following this. So object-oriented programming embodies three design concepts: encapsulation, inheritance, and polymorphism. And so if you're not familiar with an inheritance and polymorphism, you might want to look at appendices B, C, and D. We're going to discuss encapsulation as a way to hide the details of an implementation during the design of a class. We emphasize the importance both of specifying how a method should behave before you implement it and of expressing your specifications as comments in your program. We introduce Java interfaces as a way to separate the declarations of a class's behavior from its implementation. And we will also present at an elementary level some techniques for identifying the classes necessary for a particular solution. Okay, we've already mentioned this: encapsulation, inheritance, and polymorphism. And so those are some key elements that we'll now get a chance to start to dig into. So encapsulation is one of three design principles of object-oriented programming. The word encapsulation sounds as though it means putting things in a capsule, and that image is actually a pretty good mental perspective, mental image for this. Encapsulation hides the fine detail of what is inside the quote capsule. For this reason, encapsulation is often called information hiding. But not everything should be hidden. In an automobile, certain things are visible, like the pedals and the steering wheel, and others are hidden under the hood. In other words, the automobile is encapsulated so the details are hidden and only the controls needed to drive the automobile are visible. And so that's what we're trying to focus on here. And so here in this figure, we have an illustration of those things that are made available. And so what is the most useful description of an automobile if you want to learn how to drive one? It clearly is not a description of how its motor works. Such details are unnecessary when you want to learn to drive. In fact, such details can get in your way. If you want to learn to drive an automobile, the most useful description of an automobile has such features as the following. If you press the foot on the accelerator pedal, the automobile will move faster. If you press your foot on the brake, the automobile will slow down and eventually stop. If you turn the steering wheel to the right, the automobile turns to the right. And if you turn the steering wheel to the left, it will turn to the left. Just as you need not tell someone who wants to drive a car how the engine works, you need not tell someone who uses a piece of software all the fine details of the Java implementation. Likewise, suppose you are creating a software component for another programmer to use in a program. You should describe the component in a way that tells the other programmer how to use it, but spares the programmer all the details of how you wrote the software. So another thing that we can talk about, when done correctly, encapsulation divides classes into two parts, which we will call the interface and the implementation. So the interface describes everything a programmer needs to know about the class. It consists of the headers and the public methods of the class, the comments that tells the programmer how to use these public methods, and any publicly defined constants of the class. The interface should be all that you need to know to use the class in your program. So you can note that a program that uses a particular class is known as a client of the class. The implementation consists of all the data fields and the definitions of all methods, including those that are public, private, and protected. Although you need the implementation to run a client, you should not need to know anything about the implementation to write the client. So you can see that we're having a level of abstraction, and that's useful for a number of reasons. So in this figure, we're showing an illustration of encapsulation. So that illustrates an encapsulate implementation of a class and the class's interface. Although the implementation is hidden from the client, the interface is visible and provides a well-regulated means for the client to communicate with the implementation. And the implementation could be proprietary. And so this could be the way that you're trying to make this publicly available, or you could use like the car analogy that there's just a lot of details that aren't necessary. So, and then you have methods that are contained within that class. And so you have preconditions, postconditions, and assertions. So a precondition is a statement of the conditions that must be true before a method begins executing. The method should not be used and cannot be expected to perform correctly unless the preconditions is satisfied. A precondition can be related to the description of a method's parameters. For example, a method that computes the square root of x can have x has to be greater than or equal to 0 as a precondition. A postcondition is a statement of what is true after a method completes execution, assuming that the precondition was met. For a valued method, the precondition will describe the value returned by the method. For a void method, the postcondition will describe actions taken and any changes to the calling object. In general, the postcondition describes all the effects produced by a method in invocation. Thinking in terms of a precondition can help you to clarify a method's purpose. Notice that going from precondition to postcondition leaves out the how, that is, we separate the method's specification from its implementation. And then for assertions, an assertion is a statement of truth about some aspect of your program's logic. You can think of it as a Boolean expression that is true, or that is at least should be true at a certain point. Preconditions and postconditions, for example, are assertions made about conditions at the beginning and the end of a method. If one of these assertions is false, then something is wrong with your program. You can state assertions as comments within your code. For example, if at some point in a method's definition, you know that the variable sum should be positive, you could write the assertion that the sum is greater than 0. So there's a variety of things that you can be doing with that. Okay, well, let's talk about some of the Java portion. And the first thing you need to have is an interface. So earlier we spoke in general terms about the interface, which tells you all you need to know about a particular class in your program. Although a Java class intermixes its interfaces with its implementation, you can write a separate interface, and we'll be doing a lot of that as you see in this course. Java interface is a program component that declares a number of public methods and can define public name constants, such as an interface. Such an interface should include comments that specify the methods in order to provide a programmer with the necessary information to implement them. Some interfaces describe all the public methods in a class, while others specify only certain methods. When you write a class that defines the methods declared an interface, we say the class implements the interface. The class that implements an interface must define a body for every method that the interface specifies. The interface, however, might not declare every method defined in the class. You can write your own interface, and you can use those that are in the Java class library. When you write a Java interface, you place it in its own file that isn't an interface, and the class that implemented it are in two separate files. So here is an example of what we have, and so talking a little bit more about writing a Java interface. And so a Java interface begins like a class definition, except that you use the word interface instead of class. That is, an interface begins with the statement, as we see, public interface measurable. The interface can contain any number of public method headers, at each followed by a semicolon. An interface does not declare the constructors for a class and cannot declare static or final methods. Note that the methods within an interface are public by default. You can omit public from their headers. The interface can also define any number of public named constants. So this is the interface for measurable. And now we have an interface for name measurable. And so in this situation, imagine objects such as circles, squares, or plots of land that have both a perimeter and an area. Suppose we want the classes of these objects to have get methods that return these quantities, and various if various programmers implement these classes, they likely would not name or specify these get methods in the same way. To ensure that these classes define our methods in a uniform way, we rewrite the Java interface as shown here, both in the previous listing and this listing. On this one, we're showing an interface. The interface provides a programmer with a handy summary of the method's specifications. The programmer should be able to use these methods without looking at the class that implements them. Okay, here's an illustration of the files that contain measurable, circle, square, and their client. And so we're starting to get more details into the implementation. So let's talk about implementing an interface. Any class that implements an interface must state that at the beginning of its definition by using an implements clause. For example, if a class circle implements the interface measurable, it must begin as follows: public class circle implements measurable. The class then must provide a definition for each method declared in the interface. In this example, the class circle must implement at least the method get perimeter and get area. If you wrote a class square that implements measurable, the class would begin with public class square implements measurable and would define at least the methods get perimeter and get area. Clearly, the definitions of the two methods would differ from those in the class circle. So what about interface as a data type? You can use Java interface as you would a data type when you declare a variable, a data field, or a method's parameter. For example, the method give last name to is, and we spoke about before, has a parameter whose type is name interface, public void give last name to. Any argument that you pass to the method must be an object of a class that implements name interface. So why didn't we declare a names type to be a class such as a name? We want the interface to be independent of any class that implements it, since more than one class can implement an interface. By using name interface as the parameter's type, you ensure that the method's arguments will have all the methods declared in a named interface. In general, you can be sure that a method's parameters will have particular methods, namely those declared in an interface. If its data type is the interface, additionally, the parameters will have only those methods. Okay, so that's just a little bit of a perspective on interface as a data type. And interface versus abstract class, you can think about that a little bit. So there's various ways that you can also extend an interface. Once you have an interface, you can derive another interface from it by using inheritance. In fact, you can derive an interface from several interfaces, even though you cannot derive a class from several classes. When an interface extends another interface, all the methods of the inherited, it has all the methods of the inherited interface. Thus, you can create an interface that consists of the methods in an existing interface plus some new methods. So those are just some perspectives to think about. So an interface is similar to that of an abstract class, but an interface is not a class. You use an abstract class if you want to provide a method definition or declare a private field that the class will have in common. And a class can implement several interfaces, but it can extend only one abstract class. So that's just a little bit more details. So what about a name constants with an interface? An interface can contain name constants, that is public data fields that you initialize and declare as final. If you want to implement several classes that share a common set of name constants, you can define the constants in an interface that the class implements. You could define your constants in a separate class instead of an interface. We will look at both ways in this in a little bit, whichever you want to choose, but you only you have only one set of constants to keep current. So you can think of an example, say if you have several classes that you must convert measurements to a metric system, you can define conversion factors as constants, and these classes can share. And so we could place the constant in as an interface. So here we're getting into that scenario. And so we talked about specifying classes and implementing classes, but up to now we have described the classes to specify or implement. If you must design an application from scratch, how will you choose the classes you need? In this section, we'll introduce some new techniques that software designers use to choose and design classes. Although we will mention these techniques from time to time throughout the book, the intent is simply to expose the ideas. Further courses will cover ways to select and design classes in more detail. So imagine that we're designing a registration system for a school. Where should you begin? A useful way to start would be to look at the system from a functional point of view. So ask a question like, who or what will use this system? A human user or a software component that interacts with the system is called an actor. For a first step is to list the possible actors for a registration system. Two of the actors could be a student and the registrar. What can each actor do to the system? So this would be specifying some details. A scenario is a description of the interaction between an actor and the system. For example, a student can add a course. The basic scenario has variations that give rise to other scenarios. For instance, what happens when the student attempts to add a course that is closed? Or on a second step, so there's further steps you would be fleshing out as you identify scenarios. One way to do in this process to ask the question is what happens when? And then you can be thinking about which scenarios involve common goals. For example, two scenarios that we just described are related to the common goal of adding a course. A group of such related scenarios is called a use case. And then a third example would be to identify the use cases. So let's expose some of these type of methods that you can be showing this. And so here we have an approach to try to help us to choose the type of classes we'll be needing. So you can get an overall picture of the use cases involved in a system you're designing by drawing a use case diagram. So this is an example of a use case diagram. So it's a diagram for a simple registration system. Each actor, the student and the registrar, appears as stick figures. The box represents the registration system, and the ovals within the box are the use cases. A line joins an actor and a use case if an interaction exists between the two. So let's talk about identifying the classes. And so although drawing a use case diagram is a step in the right direction, it does not identify the classes that are needed for your system. Several techniques are possible. One simple technique is to describe the system and then identify the nouns and verbs in the description. So this is what we have here is sort of a narrative that you're starting to translate that into requirements. Nouns can specify classes and the verbs can suggest appropriate methods within the classes. And so we have classes and methods, things that we'll be using in Java. Given the impreciseness of natural language, so this technique is not foolproof, but it can be useful. So we could write a sequence of steps to describe each use case in the class, the use case diagram we just showed here. And that's what we're going to try and walk ourselves through. So in that figure, it gives a description of the use case for adding a course from the point of view of a student. Notice the alternative actions taken when the system does not recognize a student or when a requested course is closed. And those are some other details that you would want to figure out. Okay, here is a something called a class responsibility collaboration, CRC card. And so this is sort of a precursor to something we'll get into shortly, getting into universal modeling language notation. So a simple technique for exploring the purposes of a class is using index cards. Each card represents one class. You begin by choosing the descriptive name for a class and writing at the top of the card. You then list the actions that represent the class's responsibilities. You do this for each class in the system, and then finally you indicate the interactions or collaborations among the classes. That is, you write on each class's card the names of other classes that have some sort of interaction with the class. And because of their content, these cards are called class responsibility collaboration, or CRCs. So now we get into the unified modeling language, and we had a use case, which is one of the diagrams in the unified modeling language that we showed a little bit earlier. So designers used UML to illustrate a software system, the necessary classes and their relationships. UML gives people an overall view of a complex system more effectively than either a natural language or a programming language can. English, for example, can be ambiguous, and Java code provides too much detail. Providing a clear picture of the interactions among classes is one of the strengths of UML. Besides use case diagrams, UML provides a class diagram that places each class description in a box analogous to a CRC card. And the box contains the class names, its attributes or data fields, and operations or methods. So we're seeing an example of what it would be for a course schedule. If you represent an interface in UML, much as you would represent a class, but what you would see is in the names, it would have also listed something called an interface. So in the figure, we're seeing that type of notation and what that would be for the name of what we're trying to create an interface is for measurable. So in a class diagram, lines join the class boxes to show the relationship among classes. For example, the class diagram here shows the classes undergraduate student and graduate student are each derived from the class student. An arrow with a hollow head points to the superclass within the UML. That the superclass student is said to be a generalization of undergrad student and grad student. In a class if a class implements an interface, you draw an arrow having a dotted shaft and a hollow head from the class to the interface. For example, the class circle in the class circle, if it implements the interface measurable, and so here we're showing that relationship in the figure. An association is a relationship between two objects of different classes. And so basically an association is what a CRC calls a collaboration. For example, relationships exist among the classes, students, course schedule, and course. And so here we're showing the UML picture and the relationships associated with that. The arrow between the classes, course schedule and course, for example, indicate a relationship between the objects of the class, course schedule, and objects of the class course. The arrow points toward course and indicates responsibilities. Thus, the course schedule object should be able to tell us the courses it contains, but a course object needs not to be able to tell us which schedules it belongs. So the UML calls this aspect of the notation the navigability. This particular association is said to be unidirectional since the arrow is pointing one direction. An association between a line and an arrowhead on both ends is called bidirectionality. For example, a student object can find its course schedule, and a course schedule object can discover the students to which it belongs. You can assume that the navigability of an association represented by a line without an arrowhead is unspecified at the present stage of the design. At the end of each arrow are numbers. At the head of the arrow between course schedule and course, you will see the notation 0.10. This notation indicates that each course schedule object is associated between 0 and 10 courses. At the other end of the arrow is an asterisk. If it has the same meaning as a notation of 0 to infinity, each course object can be associated with many course schedules or none at all. The class diagram also indicates a relationship between one student object and one course schedule object. This notation at the end of the arrow is called the association cardinality or multiplicity. Okay, we'll go ahead and just finish up here with a short few comments on reusing classes. And so when you first start to write programs, you can easily get the impression that each program is designed and written from scratch. On the contrary, most softwares were created by combining already existing components with new components. This approach saves time and money. In addition, the existing components have been used many times and so are better tested and more reliable. So you can be thinking of a highway simulation program might include a new highway object to model a new highway design, but would probably model automobiles by using an automobile class that has already been designed for some other programs. As you identify the classes you will need for your project, you can see whether any of the classes already exist. You can use them as is, or would they serve as a good base class for a new class? So as you design new classes, you should take steps to ensure that they are easily reusable in the future. You must specify exactly how objects of that class interact with other objects. This is a principle of encapsulation that we have discussed earlier, but encapsulation is not the only principle you must follow. You must also design your class so that other objects are general and not tailored too much for one particular program. So those are just a couple things for you to be thinking about. Using the principles that anyway, I think I'm just going to end it there. So we had a lot of good content to give a little bit of an overview and orientation for the course and how things are organized as we proceed here. And I'll go ahead and end this lecture for here. Thank you very much.